Good morning, I'm Milena Guiar from Thornton International. Julian Thornton and I will be your host for today. After the presentation, we will have time for questions. Feel free to send your questions using the Q&A box in the Zoom page. Please use the option sent to everybody, not only to the presenter. I'd like to welcome Robin and Pierre, who will present the webinar today. Feel free to introduce yourselves and start whenever you want.
Okay, good morning. My name's Robin Bell. I'm the COO for Inflomatics, and I will run through some context for you in relation to our business. It will be very quick, and then we'll talk about some of the technical aspects of the presentation. So today we'll be talking about mitigating the damage to water networks by calming high-frequency dynamic pressure variations. I will introduce a metric called cumulative pressure induced stress. I will present first for around 20 minutes, and then I'll hand over to a good friend and colleague, Pierre Bonnadet from CPIS, who will introduce himself, and will cover another 20 minutes of principally case studies. So very quickly, our company was founded 5 years ago. We were a spin out from Imperial College. We have patented technology, and we continue to work with Imperial College on intellectual property. We have a number of key clients in the UK and around the world, and we've shipped around 3,000 systems over the last few years. We work with a few strategic partners, and I'll very quickly mention a few of them in a minute. We're a smallish team. We're around 26 people, spread around the UK and the European Union, and we work principally on a remote basis. So that's how we work, and we've grown. Our growth has tripled over the last 2 years, so we're very proud of that. All of our products are cloud-based, basically data modeling and analytics tools. Just really, I'm showing this because Pierre will talk more about CPIS, but we have deployed in more than 10 countries where CPIS operates and have a very close partnership. In the UK, we have over 2,000 deployments across some of the key utilities, and working very, very closely with those utilities, and learning a lot on both sides, I think. So very quickly, our products and services. Today, I'll talk mostly about InfloSys Edge and the case studies that have come from that. We also have a product which is Arboricity, which is built on hydraulic modeling, uses the high frequency pressure insights, and is actually a data agnostic platform, but we don't have time today to talk too much about that. Calm Network is the association with CPIS, and again, Pierre will cover that. CPIS have a minority interest in informatics. We also work with Clayval on advanced pressure management techniques, and I have one case study in relation to that. We also have a relationship with Black & Veatch, and we have a Serene product, which is about DMA, healthy DMAs. So what is InfloSys Edge? It's a low-cost, high-resolution, accurate pressure measurement device in the first instance. We give some indication there in relation to how those might be deployed. It's not hard and fast, but it gives some indication of our approaches. It's very fast and efficient to deploy, and it has the ability to do computing at the edge of the network, and that's a fundamental capability for us. And of course, we have a web application to deliver insights by what we call a network narrative. As you might expect, that web platform has event alert reporting, management. We also do event source localization. And the most important thing for us is we can integrate into corporate systems. So just a very quick summary there. Again, not time to talk in any detail. We also have secure communications. It was a very important part of our configuration, that it must be a secure platform. So let's now talk about the technical aspects of high frequency pressure measurement and the insights that can be achieved. So here we show a plot. So you can see the blue trace shows 15-minute data. Typically, this is how standard telemetry works in a network. What is missed is the red information, which here is shown at 128 samples per second, and a massive amount of detail is lost. So I've shown all of my pressure readings in PSI. We can work in PSI, we can work in meters of water. But what we see here is around 100 PSI transient pressure variations observed in this particular example. Now, here we're just looking a little bit more detail, drilling down into those missed events. So again, you see blue 15-minute data, which effectively on this scale gives 1 point. So it gives very little information. 1 second is an improvement, but it still doesn't capture the full resolution of the transient response. Then going to 128 samples per second gives, reconstructs the waveform. It's an important, in communications theory, Nyquist theory means you need to oversample. The same process is true in the water network and capturing these detail effects. So very important to have the right sampling frequency. And we have chosen 128 samples per second to be the optimum for what we're trying to achieve. So I'll introduce a metric called cumulative pressure induced stress. This was developed in conjunction with Imperial College. Following a significant period of research, we, on our board, we have Dr. Ivan Stoyanov, who is is a reader at Imperial College, and he has helped drive towards some very clear and fundamental solutions, which include this particular metric. So what we're capturing here is a cumulative effect of dominant cycles that are just not seen in the 15-minute data. We talk about pressure variability. We don't just talk about transients. Transients imply they're sort of single events, but cumulative pressure variations can be continuous effects. You see again on the left there the low speed versus the high speed data. So what does that do to the pipe? That creates pressures, stresses, hoop stresses within the pipe itself, and can lead to micro cracking. You can see an illustration there of how those pressures are uneven around the surface of a pipe. Then on the right-hand side, you can see where an asset can deteriorate. In this particular case, a longitudinal crack along a very significant main. I won't declare who the utility is, but it was a UK utility. And this, of course, caused a serious supply interruption on, in this case, a trunk main. So it's quite clear there is damage can be caused, and some samples were analysed from this pipe to assert the theorem in relation to the high frequency pressure variations. So traditionally, age, material, climate, and soils, soil types fed into burst correlations. I'm delighted we have Alan Lambert on the session today, because he clearly brought the industry's attention towards the impact of pressure, mean and maximum pressure on burst correlations. What we believe we're bringing now in terms of the high frequency dynamics is adding to those correlations with more microscopic information about networks. We did a study with, in collaboration with Imperial College, but also in Severn Trent Water, of over 700 lift and shift installations of devices capable of measuring that high frequency dynamic variation, so using our products. So just to understand, these were deployed for maybe 1 or 2 weeks in a particular location, and then moved on to another location, and we built up this database of over 700 deployments. Again, here I'm plotting PSI against miles, against burst rate per 100 miles per year. On the right-hand side, you can see what I'm showing there as greater than 20,000 PSI. Now, what that means is, in a 24-hour period, there have been excursions up and down in terms of pressure, which accumulate to 20,000 PSI. Those are very significant, very large magnitude variations, but some of those are very small variations which accumulate to get that score. We were able to correlate those numbers to burst records, which were over a 10-year plus period. So we saw, even though the pressure data was effectively now data, this related to burst records over a significant previous period, there was still a correlation, which is significant in itself, and this confirmed the damage that high frequency pressure variations can do to networks. And of course, reducing that, and it's possible to reduce by orders of magnitude, has a similar effect on the burst rates. So I'm sure many of you here have heard transients. We have a quick demonstration from me now. Then Pierre Bonnadet will follow up with a very significant real-world installation which shows these pressure variations. So I'll play it, and then I might just, well, in fact, if I say that you'll hear a big bang initially, and what's happening here is a valve is being opened in a test grid, then you'll see cavitation effects. If you watch the pipe carefully, it has a glass cover to it, so you see the air compressing, expanding and compressing. And then if you listen hard, you'll hear a little bit later, you'll hear a second bang, which is a propagation of that surge effect through the network. I'll just go back and, okay. So you can see a very physical manifestation of surge effects due to, in this case, closing the valve. So I'll move on to some use cases where we've worked with, in this case, primarily UK utilities, and then Pierre will go on to some of the worldwide cases. So I mentioned that we did this study with Severn Trent, and this was presented to the board of Severn Trent Water. We did some analytical studies to determine the potential for across the network, across the full network, to reduce those dynamic variations and achieve at least a 15 to 20% reduction in burst rate, which was relatively conservative in its nature. Those benefits were calculated by Severn Trent and presented to their board. You can see those in dollars, avoided repair costs. In the UK, we have operational delivery incentives, so ODIs, where there are fines to pay or savings or benefits to be gained by achieving certain metrics. And also there's water quality operational delivery incentives as well. We know that this improves asset health. We did a trial, as part of this trial with Severn Trent, we found that in a zone which had significant surge effects, there were very high PRV maintenance rates compared to a gravity-fed zone nearby. And of course, improve customer service if the supply interruptions are reduced. This shows by tuning the variable speed drives that are associated with this particular example, 100 PSI, in fact, peak variation in this case was reduced to less than 20 PSI. And that is a fundamental physical improvement in reducing the impact on the network. So I have here a case study for Portsmouth Water. If I try and explain, what you're looking at on a plot there in the blue is a statistical model which learns the behavior of a particular asset, in this case PRVs, which are very critical to Portsmouth, who have very few PRVs in very large zones. We compare that to measured data, and you can see two manual high and a manual low threshold. Now, what's intriguing here, if you look at the call out there at the bottom, is there was some evidence of a departure from normal operation some hours before there was a pressure breach due to the PRV not responding as it should, and multiple bursts overnight. Very interesting talking to Portsmouth Water and a gentleman called Jamie Jones, who is responsible for ensuring these PRVs are operated. having that insight would certainly allow them to make interventions to the network before issues occur. So large PRV zones, critical to continued supply. Statistical and hydraulic approaches were used to model this performance, and this anomalous behavior can be used to drive intervention ahead of catastrophe. So I now move on to a case study with Yorkshire Water, where they had very, very high cumulative pressure induced stress, CPIS. So 300,000 PSI appeared. You can see a trace on the top left there. We were then able to dissect that down into a particular zone. And then that was generated an identification by zone and by street. Then they were able to address the PIV hammering and hunting and to resolve that. And although that made a significant impact in the reduction, and they continue to reduce the CPIS in that area, the PRV actually remains oversized, and that magnifying glass there shows there are still significant variations at a significant fluctuation rate. Very quick case study here in relation to Wessex, where we were able to calm the network by implementing a calm solution in conjunction with Clayval, where we have several devices deployed in a DMA which work together, not just critical points, but understanding the hydraulics within the network, feeding that back to the link to valve solution of Clayval. So I've covered very, very quickly in the time we have available a number of case studies. So just literally one more slide, then I'll hand over to Pierre. So dynamic pressure variations clearly, indisputably damage critical assets. We can understand these effects using cumulative pressure induced stress, our CPIS metric, and it's the first step towards resolution. It is just one of the tools we have, but I think it's a very significant one to share with this audience. We're going to move on to talk about calm network solutions, working with Suez and Clayval, so Pierre has a number of those examples. And how we work together, so if there's anybody on the call who's interested in following up, we love to listen, we love to understand customers' problems, we need to understand why they have issues and what solutions we can implement. So I'd love to talk to all of you, anybody who wants to discuss in more detail. We have an approach called Inflosys Starter Kits to support deployments in critical zones and assets and start that first stage of engagement. And as you can see in the UK and also worldwide, we've scaled that engagement quite significantly over the last few years. So I'd like to thank you again for giving me this opportunity to talk today. And you have my details there, and please call me, please drop me an email, and thank you for listening. Okay. So I'll hand over to Pierre. Pierre, we can't hear you.
Pierre, do you need any help? Yes.
Pierre, you're on mute.
Yeah, you are on mute now.
It should be okay now.
Ah, there we go. Okay,
I was on mute and now it's okay. I was not able to unmute myself and I needed your support. So it's okay now. You should be able to see my screen as well.
Mm-hmm. Start the presentation mode. Yes, now it's working.
Okay.
Thank you.
So thank you, Robin. As you may hear with my accent, I'm not British, but I hope that you will understand what I'm saying. And I will present you our journey with informatics to calm the network with Suez. And I will develop the calm network approach that we have developed within Suez. So first of all, let me introduce myself. I'm Pierre Bonardet. I'm a member of a technical team, which is a Centre Technique Distribution, which is a specialist group of 20 people. And we provide expertise to our business unit around the world. So this group was created by David Duccini. I guess some of you are familiar with his name. And the idea is that in Suez, we have many water utilities, and we want to provide them support and improve their performance. And we are managing very small utilities to very big water utilities across the world. And the idea of our group is to gather feedback, to gather experience, and to develop also innovation in the field of water networks. So you have the 5 topics on which we are working. Today, we mainly focus on hydraulic performance and asset performance. And in order to deliver performance, we need innovation. And that's where informatics come. But we also need to embed this innovation into solution, into something that we can deliver to our clients, whether it is internal clients of Suez or external clients. And that's why we have developed the calm network approach. Why calm network? Is because pressure management is key to understand for pressure, for pipe degradation. It is a source of degradation of pipe together with soil condition, water quality, and so on. But it's also a source of failure, if in particular if you have a transient and very big pressure variation. So what we want to avoid is this water hammer in the network that can occur with many sources of transient. And in order to know where does the transient come from, we need this high frequency pressure monitoring device. So what is our story with informatics? As a Suez specialist group, what we do usually, we do techno tests. So we reviewed this technology and we started watching at this technology 3 years ago, 4 years ago. And there are many actors on this field. So we reviewed them. And then we are really interested to work with informatics because it's more than pressure management. It's also, they come with the CPIS as an asset management indicator. They come with the Imperial College approach, which is a more scientific approach of pressure management. So we were really interested to work with them. As Robin said, we partner with them, but not only we invested in the company, it's also a partnership in the development of the product. So we are currently developing algorithm to improve all the data analytics, because if you are managing 1 second data or 128 data per second for many pressure devices, it's a huge amount of data that you need to collect and to analyze. So we are working on data analytics. And now we are starting the deployment in our contract. So we are starting massive deployment to boost the performance and pressure management of our contracts. What is also interesting is that in the framework of pressure management, we have developed different solutions, different approach. And first, we are convinced that if we want to tackle the problem of real losses, we should not only work on the leak detection, but also work on asset management and pressure management. Because the idea is clearly to reduce the number of new leaks. And in order to do so, either we renew the pipe or we decrease the pressure and we manage better the pressure on the network. So we have developed solution to better know the risk of the pipe with NetScan, with all the asset management tools that we have. We have developed the calm network approach to better manage the pressure on the pipe. And you are also developing new approach of hydraulic models, what we call digital twin, in order to use operational hydraulic models to gain information of on the network and detect some events. And for all these purposes, we are using informatics because it's a very useful tool and very multi-purpose, I would say, tool. In terms of deployment, we started to deploy it in Suez, mainly in France, and now we are deploying it in more than 10 countries. We have started also in Australia, in Morocco, in South America, in America, Mexico, Spain, Italy, and in many contracts that we have in France. So these figures are growing, We have 800 device orders so far, but the idea is to grow and to do assessment on the most critical contract using this device. So CAM network, how does it work? We have designed a 3-stage process. The idea first is to have a better understanding on the pressure, on the dynamic of a water network and on the pressure variation on the water network. So we do what we call the network narrative. The idea is that we deploy this device on the network. And what is very useful is we can have a lift and shift approach. So we can do punctual diagnosis, or we can diagnose a DMA or an area or a full CT. And it's very easy to deploy. Once we do that, we gain knowledge on the network and we identify some mitigation action. And then comes a phase 2, where we try to eliminate transient, but also to work on pressure management and reducing pressure, reducing average zone pressure, and also better control of pressure during day and night is a part of the design job that we do in phase 2. So it's not only about transient management, it's about an holistic approach on pressure management, which include reduction of pressure, control of pressure, and transient management. And for that phase, we are also collaborating with valve providers such as Claval in order to have a better way to control the pressure on the network. And the combination of both Claval and Informatics helps us to monitor and control the network. And in order to do that, we go to phase 3, which is a more permanent monitoring, and where we use our tool for network monitoring. We have a tool called Aqua Advanced. And the idea is to not only to look at pressure data, but also to combine this data with flow measurements, with smart metering, with GIS data, and have an online monitoring and control system of the network. So that is our approach. And the idea is that informatics is fit for purpose for all these objectives. First of all, it enables punctual diagnosis of equipment. And in that case, we will do diagnosis of pump station. We will diagnose the surge protection. We will see all the PRV set points are set, all the PRV are working. We also must emphasize the impact of our operation on transient. So transient is not only a problem of a pump start and stop, it's also a problem of valve operation by our operators. So this equipment enables us also to record some behavior and to train people to better do valve operation. So hydrant testing, for instance, or valve shut off and leak repair. The idea is to do a smooth valve operation and to monitor this behavior and to train people on that topic. Then we can do a more massive deployment with a network narrative, where we will deploy dozens of devices for a network, and we will record data and analyze it. We do pressure control and design, and we will do the permanent monitoring, and also with the use of this data for other purposes, such as asset management or hydraulic models. Some REX, so REX is a French name, but it's retour d'expérience, so feedback, operational feedback on some case studies. This one is from a case studies about behavioral change. You know, when you do hydrant testing, you can do a lot of transient, you can generate a lot of transient on the network. And this is the kind of curves that you can generate when you do hydrant testing, opening a fully an hydrant on the network and generating more than 4 or 5 bar of pressure variation. So the idea is to compare this situation to a better operation where you can maneuver valve smoothly and then generate slower perturbation to the network. Because hydrant testing is a very common operation on the network, so we are generating dozens of transient every day in our networks doing testing. Another example is a pumping station operation. where we have a problem with a specific pumping station, which is a complex one, and there is 3 pumps, there is a surge protection, but we don't know if it works well or not. And there are many equipment like a check valve and other valves and other equipment that interact between each other. And we were able to record some experiments where you can see the impact or you will hear the impact of a pressure transient on the pumping station. Hear the noise, and you see the curve of pressure variation that corresponds to the first wave of pressure transient that has generated an impact and integration on the pumping station. But what is also that we have a second wave coming. The second wave is not only about COVID, it's also about pressure transient. And you can imagine the damage that it can do on the network because this pressure wave is propagating and it can really damage the network. Another example that we have is PRV. You have this wonderful curve. I think it's very nice transient curve of at 2 points of the network on a critical pipe. So that's why the pressure wave is propagating very well, because it is a critical transport main with no connection. And there is a pressure wave that starts at a PSV, so a pressure sustaining valve, and that rebounds on a check valve a few kilometers away, and it comes back, and you see this curve. And we were able, thanks to informatics, to diagnose this problem, to identify what was the cause of the problem, and to simply remove it by a better maintenance of the valve and by changing the speed of opening and closing of the valve. So in that case, it's a simple screwdriver operation that can fix the problem, or at least that can fix 70% of the problem, because in terms of pressure, we go from 10 bar to 7 bar. And in terms of CPIS, I think for this example, the CPIS was 700, and the new CPIS of the event after this operation is 100. So you can imagine that the impact is less important now than it was before, thanks to this simple maintenance of our PSV. Another example, and here the idea is that we don't do only simple deployment, we do massive deployment on some contracts. Here is in Versailles, we manage 800 kilometers of networks, and we have 45 devices installed. And in order to maximize the interest of informatics, we do a deployment plan where we are looking at different criteria to install the device on the network. So for instance, the heat map of leaks, also the age of the networks and the kind of material that you have on the network, the big consumer, because the big consumer can generate transient, and also the potential sources of transient, pumps, PRV, motorized valve, and so on. And we do this deployment plan, and then we do an assessment. We do a full diagnosis of the system, and we identify some phenomenon and root cause analysis, and then we propose mitigation action. I will focus on some action. One is really interesting is sometimes this device enables us to understand how the network behaves. And in this particular case, we had a very severe event and we suspected that this event was due to a closed valve and a reflection on a closed valve. But there was no closed valve on the GIS, but it was simply because the GIS hasn't been updated by the recent work that were done in the area. And in fact, we found that there was effectively a closed valve on a big main. And once we reopened this valve, we did not suppress the source of the transient, but we suppress the source of amplification of the transient. And you see the result in terms of CPIS, which is a good indicator to see that we have calmed the network. So this is a very good example on how the network design can amplify transient phenomenon. That's why in Suez we try to promote more open network where we have a wider DMA with less closed valve, so that we have a better also propagation of dissipation of energy and no such kind of event. Another, and I think this is my last example on this case, is a motorized valve. And you see that there is 4 devices that see a phenomenon. So there is a propagation of the phenomenon in the distribution network. And it's due to the filling of a reservoir, of a tank, by a valve. So what we did is we installed a motorized valve, and then we set up the closing, the speed of closing of the valve, so that we reduce the phenomenon, and we suppress the transient wave generated by the closing of the valve. And my last example, because I spoke about France, but we have example in other places. I like this one because it's in Tuscany and the food is really good, but also because it's a very interesting contract for Suez, which is Nova Acque. Nova Acque is a public entity and Suez is a partner of the municipality. And we are managing the network for 30 years. But you see this valve is the valve from Clavaille. I think it can be one of the first hydraulic valve installed in Italy or in this region, because it's 60 years old valve, which is operating quite well. And with Nova Acque has installed different pilots to monitor and control pressure. And now we are installing informatics to better understand the pressure behavior, and we will work with Clavaille to install a more modern controller. So this is an ongoing story of improvement of existing pressure control. So this is an interesting example as well. And you see in some place also, in Italy, we did this kind of network narrative study. And in some area, we saw the impact of changing a PRV. So here we change the PRV, and you see the impact on CPIS on 4 different locations. So we have calmed the network on this location, but we have still a high CPIS in one area. And when we look at the pressure data, it is because we have a big consumer. So we have a domestic consumption that generates this kind of characteristic curves, and that's why when we do pressure transient management, it's an holistic approach. It's not only about working with PRV and pump, but it's also understanding the way the customers takes water and the way also our operators are maneuvering the valves. So it's clearly an holistic approach. I will go quickly on that, but we have example also of the impact of the COVID and lockdown on the calmness of the network. And we can see that in some area we have calm network because we have no more activity, and we are able to monitor it with informatics. And we have ongoing developments. I will go quickly on that, and I finished in 2 minutes. As I said, it's not only useful for pressure management, but it's also useful to monitor the pressure for asset management. Robin demonstrated the link between CPIS and the burst rate, and we did similar study also. And the idea is we need to monitor our critical assets And when we do an asset management strategy, it's not only renewing the asset, it's also about knowing where are our critical assets and putting in place a strategy to improve the life expectancy of these assets and to protect these assets. And with a calm network approach, we want to calm the network and especially the most critical assets. So we have developed like tool like NetScan. It's a tool that do risk assessment on the network, combining likelihood of failure and consequence of failure. And the two outcomes are targeted renewal plan and calm network strategy. And the last topic on which we're working is about managing a lot of data. I explained earlier that it's not only about pressure management, but it's about network management. And it's very important to have tools to gather data coming from different sources. And in Suez, we have developed the AquaAdvance suite that enables the monitoring and control on the network, taking data from the GIS and also from all sensors that we can have on the network and crossing data together. So the idea for us is clearly to integrate informatics in this software, in this tool, and to propose a calm network approach embedded into AquaAdvance, and to propose pressure monitoring and network management through AquaAdvance. So thank you, and don't hesitate to ask questions. We will be happy to answer with Robin.
Thank you, Pierre. We do have some questions here. Actually, Robin already answered some of them, but I think it's important to answer it again so it can be recorded to everybody that will see it later on YouTube. First of all, just checking here because we have a lot of here. Could we able to pick up different sampling frequencies, or it's fixed at 128 samples per second?
So, I can answer that. We have chosen to sample at the higher sampling frequency so we can reconstruct the waveform. Many customers want to do the integrations, so we can subset that data down to lower resolutions very easily. In fact, in the InfloNet application, it's subsetted down to 1 second subsets, min, max, and mean, where the user can then request the raw data at 128 samples per second. We feel it's important to always monitor at the high data rates, and we've chosen not to reduce that. We can, but we choose not to, just so we don't miss anything in the analyses we do.
Okay, Romeo is asking regarding sample gathering, how many inflow devices are required for the efficient monitoring of our assets? Is there a minimum required per distance?
It's an interesting question. What we often do, and you saw some examples from Pierre, where the network is significantly populated with devices. If we do that, we have a better understanding how the network is performing and can then depopulate to achieve an optimum deployment. So that's how we prefer. In a typical UK DMA, district metered area, often the deployments are between 4, 5, 6 devices per DMA to give some indication of the performance of that DMA. So it could be on the inlet, critical assets, key users, critical points, AZP points, and so on. So it does vary depending on the outcome that we're looking for. So I would say, yes, it does vary, but hopefully that gives some guidelines. And maybe Pierre, you have something to add to that?
Yeah. Would you like to
No, it's okay. You've covered it, Robin.
Okay, I've covered it.
Now, David Pearson is asking specifically to Pierre. Pierre, can you expand on your words on an early slide which says, identify origin of pressure transient and your network narrative. I'm thinking on my experience where the source was a single industrialist takeoff through a solenoid. I like the example of an intentional closed network valve.
Yeah. Thank you, Dave. So for the last comment, I like this one also because we always consider that we have perfect networks, but when we start digging, we find a lot of closed valves in our network. So this is a particular useful tool, informatics and high frequency pressure monitoring, because we see the propagation of the waves, so we are able to see if the network are connected or not. And sometimes we have closed valves that are open, or we have open valves that in fact are closed. So it's a good way to better know about the connectivity and the hydraulic of the system. Regarding the origin of pressure transient and network narrative. At the end, what we measure with pressure is the variation of pressure at some point. And our goal is to come back to the source. But what we consider, and this is our experience, that when we densify the amount of a monitoring device, of informatics device, with the analysis of data, we are able to better identify the source, because it's all very precise in terms of data sampling, but also data timing. So if there is a good timing, there is a delay between two devices, and we can identify the device that is closer to the source, that is the closest to the potential source. So this is very useful. And also, if we get data from other sources, so our idea is not only to use pressure data, but to use other sources of data, because we are managing the network. So we have access to SCADA system. We have access to the automatic meter reading and automatic meter infrastructure. So we have access to the consumption of customers. We are able to cross-check data and to identify that a particular customer or a particular event at some places have generated an event. So our goal is clearly to identify the sources of event, and obviously we have simple sources. A pump start and stop or a PRV operation is quite easy to understand and to find. And once we have done that, we try to find the other non-easy source of transient, such as customers, such as valve operation and other operation on the network.
Thank you, Pierre. Ian Rogers is asking, you mentioned that your solution is cloud-based. Do you offer on-premise installation of the software?
So what I talked mostly about today was InflowSys Edge. Today, that is an Amazon Web Services hosted solution. Our Arboristi solution is an anywhere deployment. So that could be on premise, that could be on other clouds. So we would value a discussion with customers in relation to what they require. We recognize that is important. There has to be some flexibility in deploying the solution for various reasons. So yes, we can, but that would be the Arboristi platform.
We don't have other questions. Julian, would you like to say something?
Sure. I could say something for the next hour, Melanie, but I'd just like to say thanks. I thought it was a very good presentation, and you know, for me, I learned a lot. I particularly like the CPI. I think the cumulative index is very, very interesting, and something which I haven't really seen before. So it may have been around for a while, but that certainly brought my attention to the problem. So very interesting, guys. Thanks very much.
Good, good.
We do have time for some other questions, but I think that's it.
Well, let me just ask then if that's it. If there's no other questions, and let everybody else discuss, please. But I was interested to see you had a pin in Brazil. Are you working in Brazil? And Milady and I do a lot of work in Brazil. Be interesting to hear about anything you're doing in the area.
Yes, we are. We have some deployments in Brazil working with Suez. Pierre, can you add anything to that?
Yeah, I don't know particularly the Brazilian case, but we have some contract. We have, as I said, we are offering this solution through our traditional contract, which are concessions contract, but we also develop a new kind of contracts, services contracts all over the world. So this kind of contracts that we have in Brazil. I know that in another topic in Brazil, Suez had won some contract about non-revenue water management in Sao Paulo, I guess. So we have many contracts, and our local team is developing a lot. So we have some operation in Brazil. We are also deploying it in Mexico, in South America, and we have operation in Colombia. So we are quite present in South America as well. Even if our stronghold is Europe, we are present in other geographies, as I mentioned in my presentation.
Okay. Thank you.
I think that is it. Just have to say thank you, Pierre. Thank you, Robin. If you would like to say something and bye everybody. Oh, we have another question here. Please, could you elaborate on your experiences with different materials, in particular cast iron versus ductile, or PVC versus poly? I don't know how to say that in English, Julian.
Let me look quick. Let me take a look here.
Ductile or PVC versus PE. Polyethylene something.
So okay, we've seen the devices, or we've had the devices deployed in many different networks. It's probably fair to say that there is a significant amount of cast iron deployed in the UK, but we have come across the different deployments. The mechanisms are similar in relation to how the high frequency, those dynamic variations can affect those pipes, but the outcomes can be somewhat different. In terms of, I'll just group them, plastic pipes. We have an interesting conversation with Portsmouth Water, who have many plastic pipes, and that is a priority for them to understand in terms of their mechanisms. So the technology is applicable to both. The study you saw was predominantly cast iron pipes, but certainly the damage to not only the pipes, but to the assets connected through the network is consistent. So the technology has applicability, but it does have some specifics depending on the pipe. And again, Pierre, I don't know if you want to add something to that.
We also have a lot of experience with cast iron. We have a lot of cast iron, and we know that it's the most fragile material, the edged cast iron. But plastic material are of concern as well, because many service connections, especially in France, are in plastic material. So there is an impact on not only on pipe, but on service connection also. And we should look at transient management and pressure management, not only for pipe, but for service connection. And especially because also the diameter is smaller, and very often the resistance of smaller pipes is less than the bigger diameter pipes. Yes, we have some topics in France, especially with polyethylene, with the old polyethylene, what we call the black polyethylene, which was installed in the early 80s or 70s, which is particularly fragile, and especially for service connection. So everything that is related to pressure has an impact on this material. I think the main difference is that for metallic pipes, there is an impact with the mechanical stress on the pressure variation, but not the average pressure. But for plastic pipes, even the average pressure has an impact on the lifetime of the material. But of course, the average pressure plays a role in the burst rate of metallic pipe. But for plastic pipes, it's even worse. And higher pressure, higher temperature, and higher disinfectant chlorine rate decrease the lifetime of plastic pipes, and pressure transient as well.
Thank you, Pierre. So we don't have any other questions. I'd like to thank you, Pierre. Thank you, Robin. If you want to say something else, then we can close the session now. Say bye, everybody, or something like that.
Yeah, I'd just like to say thank you for the opportunity to discuss this fascinating topic where there are new discoveries every day. That there is some leading research we're doing with CPIS, that we're doing with Imperial College London, and we're by no means done. That there's a lot still to do, and we look forward to working with new customers. Maybe some of you on the call want to engage further, so please do get in touch.
Okay.
Okay.
Great.
Thank you very much.
Thanks very much.
Thank you.
Stay safe, everybody.
Bye-bye.
Bye, everybody.
Bye-bye.